Hey guys, welcome to today's version of AP Physics. Hopefully last time your problem's dealing with both the speed of sound based upon temperature and also the Doppler effect. Both of those hopefully went okay for you. Today we're going to kind of retrace our steps a little bit and we're going to talk a little bit about interference. Now, if you recall, we were having interference when we'd slop that slinky down one end and it would reflect. And sometimes we would get areas of constructive interference where the crests would amplify each other, or we'd get areas of destructive interference where they'd cancel each other out. Now the way we get constructive interference is if the waves are off by multiples of lambda. It could either be off by one wave or two waves or three waves. And when that happens, if it's an even integer, these crests are going to march in tandem with each other, and we add these two together, we're going to get a bigger amplitude than we normally would. Okay? If, however, we have these waves that are offset by half of a wavelength, by half of a lambda, now we're going to get areas of destructive interference where they're going to cancel each other out. So what does this sound like? Those of you who are in band, you may kind of understand this. So because you probably have to tune your instruments together. So here we have two, it might be tough to see, but one of these waves, the red wave, is vibrating at a frequency of 50 hertz, whereas the blue wave is vibrating at a frequency of 60 hertz, about 10 times more per second. What that means is that 10 times per second, we're going to hear areas where we're going to get constructive interference and areas where we're going to get destructive interference. And since these are off by 10 hertz, we're going to hear kind of this wavering of 10 times per second. Let me show you what I mean by that. So here, if I start with two waves that are of the same frequency, here I've got 250, 249.9, close enough. They're all going to be kind of in step with each other. If, however, I change this to 260 hertz, where they're off by 10 from each other, you're going to hear and you're going to see when that happens, you're going to see areas where we're going to get constructive interference and destructive interference. What does it sound like? Hopefully you can hear that kind of wobbling sound. That's because we have 10 times per second we're hearing that. The closer these get to each other, now we should be hearing one every 2.5 seconds. Okay? The further off we get, the more we're going to get those wobbles. Okay? Now, it just so happens that I have two tuning forks here. Let's turn this off. It's starting to get annoying. Okay? They each say 288 hertz. Okay? I don't know if you can see that. It says 288 here. It says 288 here. But if you hear and listen carefully, you'll notice that they are probably very slightly off. You're going to hear where one's going to go up and then down and then up and then down. They're close to each other, so the beats are pretty far apart, but we're still going to hear that up and down in volume. So that's going to be sound interference. And the way to calculate that is fairly straightforward. All you have to do is the frequency of the beat right here is going to equal the difference between those frequencies. So if I'm off by 10 hertz on my frequencies, I'm going to hear 10 beats per second. So that's one idea today. The second idea I want to talk about today is the idea of the intensity of a sound wave. Okay? So when we have a sound wave that's being propagated, one thing you've got to presume is that this sound wave is being propagated off in all directions, kind of like what we were showing with the Doppler effect. But we do not live in a two-dimensional world. We live in a three-dimensional world. So the sound, if you'll bear with me, imagine if I've got a sphere here. And since you guys didn't just fall off the turnip truck, you understand that the volume of a sphere is going to be 4 pi r squared. So my intensity of sound is going to equal the power of that sound over this area that is trying to be covered here. So intensity equals power divided by area, and what we're going to do is we're going to measure that in watts per square meter. And since the area is 4 pi r squared, that leads us to something called the inverse square law, which we've seen before. Which means that if I double the distance that I am from a sound, it's going to cut the power in 1/4. Now, in an ideal world, we would relate this to talking about the decibel level of sound. We're not going to get to that this year. That's kind of an added kind of dessert that I can normally throw on there. This year we got to be about kind of getting through stuff. So information about this, however, is going to be found in your reading today. So what I'm going to ask you to do for next class is there's very short amount of work by assignment, but there's also going to be a little lab that I want you to try using your cell phones. Try to complete that by April 6th, and then next time we're going to talk about interference on both strings and in pipes that relate to the music that you guys make in band. Okay, that'll be next time. See you guys later. Have a good weekend.